The next category of optimization problems we're going to look at are linear constrained problems. So in this case, the objective function and all of the constraints are going to be linear equations of the input variables. So we're going to learn a little bit about how that's solved by looking at a graphical solution. And so we're limiting ourselves to 2 independent variables so that we can do that graphically, but we'll learn some things about linear constrained problems that can be applied generally. So again, we've got constraint equations, and in this case, here's what we're trying to do. We're trying to maximize the value of y that's defined by these 2 independent variables, x1 and x2. And we have 3 constraint equations. x1 has to be greater than or equal to 3, x2 has to be greater than or equal to 1, and 2x1 plus x2 has to be less than or equal to 10. Now, let's plot up the constraint equation. So we've got, since there are only 2 variables, we're plotting them on 2D space. We have x1 on the horizontal axis and x2 on the y-axis. So that shaded region contains all of the values of x1 that are greater than 3. We add to that our second constraint equations. x2 has to be greater than or equal to 1. So now that blue region is everything that would meet both constraints. And now that third constraint equation ends up being this diagonal line. And so now everything to the left of that would meet this third equation. And so the region that's shown in blue, those are the values of x1 and x2 that meet all 3 of those constraints. So there's my feasible region of solutions. Now, remember the objective function. Here's what we're trying to maximize. And let's start out by just assuming some value of y. And so, a lot of these solution methods require us to start with a guess value, so we'll just arbitrarily pick a guess value, y equals 4. And we can write the equation in the form of a line, that is, y is equal to mx plus b. So in this case, x2 is equal to 3 halves x1 minus 2. And so you can see how that plots as it passes through the feasible region. Now, because we're looking at linear problems, if I pick a different value of y, my lines that represent those equations, that equation will be parallel to the line we just drew. And so we can show for different values of y that the greatest value of y that has a line that passes through the feasible region and passes through only at that corner, that gives me the optimum solution. So in this case, x1 is 4.5, x2 is equal to 1. That is that produces a value of y of 11.5, which is the greatest value of y that I can have, where x1 and x2 still meet all 3 of our constraint equations. So what was interesting about that is that that value of y did occur at a corner point of the feasible region. And that's true even if you have more than 2 variables, even though you can't really show them on a 2-dimensional graph like that. But the extreme values always occur at a corner point. In fact, if we look here, if our desire was to minimize that objective function, we could see up at this corner, that would be the value where y is equal to 1. That would be the minimum value of that value of y. Now, let's look at a different constraints here. Well, excuse me, the same constraints and a little bit different objective function. So if we're trying to maximize y subject to these constraints, well, in this case, the line corresponding to y equals 20 ends up being along that whole side of the feasible region. So we still can find that y equals 20 is going to be the maximum value that we can get out of y. It's just that there are more points at which that occurs. And finally, one more, if I remove one of the constraints, then that's going to be an unbounded region. And so my values of y keep going up as we go to the right. So there's not a solution to the maximization problem. But if I wanted to minimize that function, you could see once again that corner point does present me with the minimum. So we're not going to actually do any graphical problems like this. What we want to come out of that, though, is that if you have a constrained linear optimization problem and you have a closed region, the constraints are such that you have limits on your variables, then you're going to end up with a solution that occurs at a corner point of the region. And again, if you have an open region, then you still might get a corner point, or maybe it's unbounded and there's no solution there. But also remember this, the solution may not be unique, that more than one corner point may yield the same optimal value. But there are numerical tools here. In Solver, we're going to use what's called the simplex method. And the simplex method, again, applies only for linear constrained problems. And so it's only looking at the points where it is feasible for that to occur. So the more variables we have, the more the simplex method is efficient for finding the solution. But again, it only works if you have linear constraint problems. And again, that is built in as an option into Excel Solver. And so we'll work a problem later on that has about a dozen independent variables. But because everything's linear, we're going to specify the simplex method to make sure we're getting the correct solution. MATLAB does have some toolboxes, but they don't have a similar function within the standard toolboxes. So when we look at these these constrained problems, really pretty much we're going to be concentrating on Excel Solver from now out. So that kind of tells you about linear constrained problems, and now we'll look to the more general solution of nonlinear constrained problems, which is most engineering problems. And again, we'll be doing those in Excel Solver. So the next video, we'll come back to that one where we're trying to optimize the dimensions of a beam.